This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
Hello, this is Adam Gordon Bell for Software Engineering Radio. Today, I'm speaking with Thorsten Ball, author of Writing an Interpreter in Go, as well as at sequel Writing a Compiler in Go. Thorsten lives near Frankfurt, Germany, and he loves to deep dive into programming topics like programming languages, interpreters, compilers, systems programming, and databases. Thorsten, welcome to Software Engineering Radio.
Hey, thanks for having me.
So today I want to talk to you about interpreters and how you might build an interpreter. So I thought a good place to start is, what is an interpreter?
Oh, that's a good question. The easiest answer is probably that interpreter is a computer program that makes a computer understand a language it didn't know before. It takes input in a specific language, let's say JavaScript, and translates it to something that the computer already understands, either by interpreting it or internally translating it or doing something else. But the basic idea is it takes in something and translates it while reading in something into something that the computer understands.
So how does an interpreter differ from a compiler?
The lines are blurry, to be honest. Like the more advanced or more industrial grade an interpreter or a compiler is, the more they, get similar to each other. But the general idea is that an interpreter takes the input, a programming language, and interprets it, meaning it does exactly what the input language tells us to do. For example, print hello world while reading the input, right? A compiler, on the other hand, translates the input language into another language, which can then later be fed to the computer to be executed. So it's a difference in when the code that you give your interpreter or the compiler will be executed. And the easiest analogy that I always use is that interpreting and compiling can be, seen as talking in a foreign language to a friend, where you have another friend that understand or translates for you, right? So let's say you have a friend that only speaks Spanish, but you don't speak Spanish, but your friend speaks English and Spanish. So you talk to your friend in English, and interpreting would mean that he listens to you for a sentence and then translates your English into Spanish. Compiling would mean that he listens to all of what you have to say in English and then writes down the Spanish translation and hands it to your second friend, which only understands Spanish. Does that make sense?
Yeah, that's a great metaphor. So like if I'm Ruby code and you're the Ruby interpreter, so what you do is you're translating it from Ruby, which I know, to whatever, either machine code or...
Yeah, exactly. So the computer understands only machine code, right? So that means in order for us to be able to talk to the computer in another language, we have to write something in machine code that takes in this other language and, interprets, translates it for the computer so the computer understands it. And, you start with machine code, but then you can, bootstrap yourself up, and then you end up with, for example, Ruby, which is an interpreter that is written in C, like the most commonly used Ruby implementation is written in C, which the computer understands because somebody wrote a C compiler before, right? The computer doesn't understand C, so somebody wrote a C compiler initially in machine code that takes in C code and outputs machine code. So now you can, write C code and the computer can understand, which means execute it. And once you have the C compiler, you can write a Ruby interpreter that is written in C that takes in Ruby code and outputs C, or interprets it on the fly and does exactly what the Ruby code instructs it to.
So Ruby is an interpreted language and C is a compiled language.
Right.
Like what about Python? So when I run a Python script, it makes like a PyC file, and then I think it executes that. So where does that fit?
That's exactly where the lines get blurry. So this is also the case with Ruby, except that you don't see it because it doesn't expose the cached result of its work. But when you see a PyC file, that means that the Python interpreter takes in Python code and it translates it to another language, and that language is called bytecode, right? And this bytecode it's bytes, but it's another language that the Python interpreter understands. It's a more denser language, like it doesn't have all the fluff and the bells and whistles. Basically, it's a stripped down version of the Python code that you put in. And what the Python interpreter does is it takes your Python code, translates it to bytecode, and then it caches this result by writing the PyC file. And then it executes what's in the PyC file. So the next time you run your Python code, the interpreter can see, okay, this is the same thing that I just translated to bytecode, and it's in the PyC file, so I can use this and directly execute the bytecode. I don't have to go through the Python to bytecode stage again.
And it's interesting because it when you describe it that way, it sounds a lot like the JVM.
Yeah,
which is so the JVM is considered a compiled language, right? It produces this bytecode, but then in fact the JVM is interpreting this bytecode, right? So in some ways, what's the JVM? Is it compiled or interpreted?
Yeah, the JVM is the Java virtual machine, and a virtual machine is a piece of software that acts like a computer. And that means the computer is a machine, right? And a virtual machine is a machine written in software. And that means it emulates what a machine does. And what a machine does in this sense is it reads in code, machine code, and executes it. It's when you get down to it, it's really simple. All the computer really does, and I'm doing air quotes here, right? All the computer really does is it reads in code, and it starts executing every instruction in this code, like add 1, add 2, print, whatever, right? And then when it says jump or go there, it executes this. But it's pretty stupid, but it just does this really good, this one thing, like executing code. And a virtual machine does exactly this. It reads in code instructions that are kind of close to machine code, but depending on what you want to do, they slightly differ. We can go into this in detail. But what it does is it reads in the code and it executes it. And the Java virtual machine is such a virtual machine that executes Java bytecode or JVM bytecode. I guess nowadays it's agnostic. It doesn't have really anything to do with Java, except of course that it's specialized for Java and stuff like this. But what happens when you run Java code is that your Java compiler takes in your Java code and it outputs JVM bytecode. And this bytecode you then feed into the JVM. And this JVM, it is itself written in, is it written in C++? I guess.
I think it is. There's a couple implementations, but I think they're all C++.
Yeah, I guess. So the JVM itself is written in another language, right? It's which a computer understands, and it's a piece of software that takes in Java bytecode and just executes it, like really in this stupid way. Take the first instruction, execute it, take the second instruction, execute it, and so on and so forth. And the reason why you want to do this is because this bytecode, it allows you to basically strip down your Java code into a really dense format. And once you have this format, you can start to optimize it, right? And you can start removing bits that you don't need, which you can only see at this level of representation, basically. And you can tune the JVM to only do this thing, like executing bytecode really, really well. And yeah, that's basically the idea behind the JVM.
So it's like Java is a compiled language, but the JVM is kind of interpreting the bytecode.
Yeah, exactly. And it gets even blurrier than this because you compile Java, you compile it to JVM bytecode, and then the JVM interprets this bytecode, right? So you have a compiler, but then you have an interpreter. But here's the thing: the JVM is so optimized that while it interprets the bytecode, it sometimes, and I'm not sure exactly when it kicks in, but it sometimes takes in the bytecode and in the background translates it to machine code. It doesn't interpret it, but it translates it to machine code. And once it has this result of this compilation, of this translation, the next time it executes the same piece of code, it doesn't interpret the bytecode, but instead executes the machine code. So while it's running, while it's interpreting, it's at the same time compiling. And this is called just-in-time compilation, because it's not, it's opposed to ahead-of-time compilation, which is what we usually think of when we think of compilation, that you compile a piece of code ahead of time. That means before you want to run it, and then you execute it later on, right?
Yeah.
But the JVM, it compiles it while it's running and then executes it immediately after compiling. And that's like we have like a compiler in there, we have an interpreter in there, then we have a compiler in the interpreter, and then basically the computer again acts as an interpreter of this generated machine code. So it is blurry, right?
So it's like the line between compilers and interpreters, it's almost like a spectrum rather than two baskets.
Yeah. I mean, of course, there's general, these two categories of how you can execute code by either interpreting it, which means, reading in stuff and then doing the stuff, or by translating it into another form. So there's these two ideas of how to execute code, basically, these two categories of what you can do. But in production implementations of programming languages, these two get mixed all the time for a specific purpose to get the best performance and stuff like this. And this is where it gets blurry.
From my outsider perspective, having not built an interpreter, it seems to me that like most interpreted languages are like dynamically typed and most compiled ones are like statically typed. But is that have something to do with the implementation, or is it unrelated?
It is related, and that is, it often has to do with like how much time you have, basically. So let's say you're compiling a program ahead of time, for example, a C program, right? You compile it to a binary, and then later on, like 10 minutes later, or 10 days or 10 months or years, whatever, you execute it. If you're not, stressed for time because you want to execute it immediately, then you can do all sorts of things. You can do optimizations. That means you're compiling the code, and while translating it, you go over the translated code again and again, and you remove, the unneeded stuff, the stuff that's useless. For example, let's say you write code that, you define like 3 variables or stuff like this, but you only use 2 in a loop, and you always increment the third in the loop, but without using the result. A compiler translates this code, then goes over the code again and again, and it detects that you actually don't need the third variable, so it throws it out of the code, right? That's an optimization.
Yeah.
Like dead code elimination, it's called. Now, doing this, like going through the code and analyzing it and throwing stuff out, or maybe moving it around or shortening it or lengthening it, whatever you want to do, this takes time, right?
Yeah.
And if you have an interpreter and you get a program in, and your goal most of the time is, right, executing it as fast as possible. Like you want to put your stuff in like Ruby, right? You don't want Ruby to wait 2 seconds before it starts executing your code. You want Ruby to immediately start running your code. And adding optimizations, this takes time, right? And so if you have a compiler, you are free to add some bit of time, right? Of course, you don't want to take it, you don't want your compilation step to take a really long time. So there's a trade-off. But in the general sense, with a compiler, you have more time to analyze stuff. And with an interpreter, the focus is largely on executing as fast as possible.
There's a trade-off between compile time and optimizations, right?
Yeah.
The more time you have at compilation, the more you can look for. But like an interpreter has 0 compilation time, so it can do 0 optimizations.
Exactly. That's the rough idea. And if you look at different programming language implementations or programming languages, you can see that they all make different trade-offs in this regard. For example, Go, they're famous for not doing a lot of compiler optimizations. There are certain optimizations that the Go compiler could do, but the authors of Go said, no, it adds too much to the compilation time. We want our compiler to be really fast. We can't do a lot of optimizations and stuff like this. And even now, where you have the debates about adding generics to Go in Go 2.0 or something, like the idea of 2.0, there's always this idea that, hey, if we add generics, how much does this add to our compilation time? And there's other languages They just don't care about compilation time because the result is highly performant code, right? It's a different trade-off you have to make.
So in your book, you use Go to build an interpreter for a language that you've created.
Right.
So why did you choose to use Go?
In hindsight, I could say for all these different reasons, but the actual reason back then was that I really enjoyed using Go. But now, I enjoyed using Go. I used it for a lot of projects that I did at the time for CLI stuff and for some systems programming. And I also didn't want to use Ruby because I feel like that Ruby kind of glossed over things. Like Go doesn't offer a lot of the niceties of Python or Ruby, for example. It's a pretty bare bones language, and I wanted to really get down to the bare bones level and not have any magic, not have any hidden stuff, no secrets, no surprises. I want to get down to the real thing, and I didn't choose C because I didn't want to worry about memory management, basically. But that being said, these were my original reasons. But nowadays, when I look back at my choice of using Go, I'm really happy that I went with Go because it turns out that Go is extremely readable, even for programmers that have never programmed in Go before. I get emails, a lot of times from readers who went through the books and they implemented their own interpreter while reading the book, but not in Go. They actually choose their own favorite language like Haskell or Rust or C# or whatever. And this is amazing. Like I'm pretty sure that if I had written the interpreter or the compiler in Ruby in the code and written idiomatic Ruby code, that it wouldn't be so easy to understand and translate for non-Ruby programmers as this Go code is. And also, like besides the readability aspect, there's another good reason for Go, which is that it comes with a lot of stuff. Like we don't use a lot of stuff in the book, to be honest. Like there are no third-party libraries. We only use the standard library and not a lot of the standard library actually, but it comes with its own testing framework, right? And it comes with, you can easily compile the code with the built-in tooling. You can run the tests with the built-in tooling. You have Go format, which is this tool that format your Go code to the one true standard. So it's not that, it's not the situation that people read through my Go code and they go, how does he format? Like, why does he have the commas here? Or why does he have the braces there? Like, it's standardized. Like, it looks like every other piece of Go code out there. Nobody has to worry about formatting stuff. It's really easy. And nowadays, a lot of other languages have this. But looking back, it's like, yes, this makes total sense, especially if you're writing a book for other people to read, to have a standardized style of coding, basically.
Yeah, it makes... So I found what you're describing to be true. Like in some ways, Go is like a lowest common denominator. It doesn't have a lot of fancy stuff, right?
Yeah.
So I did actually write a version of your interpreter, and I was using Scala, which is kind of my go-to language.
Mm-hmm.
And I found it to be a lot more concise, but I think that it would be hard to follow if you didn't know the language because it's using a bunch of like idioms or something.
Yeah.
The same with Ruby, right?
Yeah. But you said it's much more concise, and I would bet that if I wrote the same code in Ruby, it would be a third of the size. Like that. Yeah. That's my bet. And I also bet that I can get even lower because in Ruby, you can write a really dense program, but then it wouldn't be readable, right?
Yeah.
And even if you do not go, this down this road of code golfing where you make it as dense as possible or as short as possible, even if you do not set out to do this, then the Ruby code would still be much denser and it would still contain maybe more stuff that readers need to understand. And it would be harder to understand for non-Ruby programmers. And I guess the same is true for Scala or a Scheme or Lisp or Haskell.
Yeah. Go is like, in some ways, like it seems to me, it's like Java. Like it's somewhat verbose, but not complicated.
Yeah. It's the same. It's like pseudocode, right? You can write the stuff like piece of code in Go, and you can hand it to somebody else. And even if they have no idea about Go, they can probably guess what you're aiming at, right? It's the same with Java, except that it's more stripped down, I would say.
Yeah. So you were mentioning, the lines of code. So how big does this interpreter end up being? Interpreter sounds like a daunting project. How much Go code does it end up being at the end?
I actually looked this up like a week ago, but I have to be honest, I forgot the exact number. But in the first book, The Interpreter, it's 3,000 lines of code, and that includes tests, because the whole book, or both books, are written in a TDD style. That means test-driven development, which means we always write a test first that fails and then write the implementation. So if you go through the books from start to finish, what you have is, in the first book, an interpreter, and the second book, a compiler and a bytecode virtual machine, and all of it is tested. So, and as we said, the Go code is not really dense, right? It's not concise. So it's 3,000 lines in the first book, and I guess another 3,000 lines in the second book, and you can subtract half of it. That's just the tests, basically. So when you get really down to it, it's not a lot of code. In the first book, it's really not a lot of code, and I'm always surprised. I'm looking and I go, how did this get into 240 pages, right? Yeah. But when you have to explain every line of code, that adds a lot of pages to a book.
So this, it's impressive how small it is. In the language that you're building an interpreter for, would you say it's like a toy language, like adding numbers, or is it a realistic programming environment?
The language is called Monkey, and I specifically set out to not, I didn't want Monkey to be a toy language that, only does, I don't know. There's other toy languages, like esoteric languages that can only print out numbers and they can only print out letters or whatever. I wanted Monkey to be as real as possible. That means as close to the languages we use on a day-to-day basis as possible. And Monkey looks kind of like JavaScript. That means it has braces, right? It has different keywords, so it doesn't have function. Instead, it has FN, because I wanted it to be more concise. It has let statements. It has, arithmetic. It has strings as data types. It has arrays, hashes. It has recursive function calls. It has closures, which is the most interesting feature, in my opinion, in the book. It has, of course, if it has closures, it has to have that. Like, it has first-class functions, higher-order functions, built-in functions, and you can basically communicate with the outside by printing "Hello World," right? That's the end of the, sorry, this is a spoiler, but the first book ends with, printing "Hello World." So sorry if I spoiled the ending there for you, but that's the ending of the first one. And in the second book, Monkey basically stays the same. So it keeps the same set of features. The language does not change. And that's, exactly what we want, because we keep Monkey the same, but switch out the implementation, right? Which is another interesting thing about languages, that, you can have the same language implemented in a totally different way. But what you put in and what you get out is the same, except that everything in the middle is switched out.
Yeah, when I think of, I guess this goes back to our interpreter versus compiler talk. I think of like a language either being one or the other. But so you're saying that it's actually unrelated to that. It can be a separate issue, the implementation.
Yeah. But with the added asterisk that there is some stuff that I think you can only do with compilation. This is like, I'm out of my depth here, but basically, if you have some super advanced type system stuff, right, or I don't know, optimizations and stuff like this, you have to go one way or the other. Like, it's not totally independent, I would say. But I guess some listener that's, a proper computer scientist will say, no, there's the general law that maybe this is, I don't know. But it feels to me like there's some really specialized thing that you can either only do in one thing or the other.
Makes sense. So if I'm going to build a interpreter, like, what are the steps in my interpreter code?
Roughly, I would say you first have to lex the input. That means you have to have a lexer, which takes in your source code as a string, basically. So it opens a file and reads a string or bytes, whatever you want to call it at that point, and it turns it into something called tokens. And tokens are basically, the representations of your source code that's easy to handle. So, for example, instead of having, I don't know, the string let foobar equals 5, semicolon, you instead get tokens that are let, then, I don't know, identify your foobar, then equals then integer 5, then semicolon. Think of the lexer as turning your one single string into a list of objects or tokens or whatever you want to call it, which is much easier to handle once you have to go about, what comes after this, or does this come before this and stuff like this when you have to analyze the source code, right? It's every programmer that ever had to deal with strings knows that a proper data structure is much easier to handle than a single string once you have to get into the inside of the string, right? So that's the first part. You have a lexer that takes in source code and turns it into tokens. And then you have a parser, and the parser takes in the tokens and it turns it into something called an abstract syntax tree, or short AST. And the AST, as the name suggests, is a tree data structure. That means, you have a parent node, for example, you have child nodes, and you can walk down the tree and analyze it. And what the parser does is it takes the tokens and looks at them and turns it into different little subtrees of this AST. For example, a let statement might be a node in a tree, and it has two child nodes. One is the identifier, which is on the left side of the equal sign, the name of the binding that you want to create. And then you have another child node, which could be, value or expression, which is what's happening on the right side of the equal sign, right? And if you put this in a tree structure, it gets super easy to work with. It's better than the tokens, right? And if you have to interpret the code later on, you are happy that you have a tree, because suddenly you can go, what is this? Like, is this a let statement? Okay, then give me the left part, or give me the right part. Or, you can easily access different parts of your program, basically.
So we start with the string, right? So we have a string that is our program, right? And then so the lexer turns it into a list of tokens.
Yeah.
Right. So the string let x equals 7 gets turned into a list of tokens. And then the parser takes that and turns it into a tree where it's like let at the top and then x on one side and 7 on the other.
Right.
The parser seems more complicated than the tokenization process. So
yeah, it is.
it is. So like I'm used to parsing, like you talked about, like a JSON document. If I receive one, and then I turn it into some sort of internal representation. But the internal representation is very similar to the actual document itself, right?
Right.
The parsing, like a programming language, seems different somehow from that.
Yeah. Yeah.
In that the representation is not, like, it's a whole different data structure.
Yeah, exactly. But to be honest, if you, it's hard to see, but if you really look at your code and, for example, I don't know, let's say you have a piece of JavaScript code and you have a for loop, right? Mm-hmm. And then you have like for the keyword, then you have opening parens, then you have like the initializer, then you have your, the condition, and then you have your step, basically. So I equals 0, then I less than 10, and I plus plus, and then you have the closing paren. Then you have the opening braces, right, that delimit the body of the for loop, and then you have the body that, I don't know, console log I or something, and then you have closing braces that end the body of the for loop. Now, think of the braces as, for example, an object in JSON. Like, they signify that this is now one level, nested deeper, right? Mm-hmm. And then your parens that come right after the for keyword, that's also one level deeper, right? And you can kind of see this in your code, that you have a structure that's repeated all the time. You do indentation, right? And you have, for example, you nest your code. So you have functions nested in other functions. You have, loop bodies nested in other loop bodies, which, if you squint at it, you can see, hey, you can probably represent this as a tree data structure, right? Because you have these different elements that are repeating, which means there's a schema to it. And then you can see that, yes, you can nest them, right? You can say this one here has child elements, like the for loop has the child element of the for loop body, for example, and it has child element of for loop condition or for loop initializer, and it itself, the for loop tree representation, can also be nested and be the body of another for loop node or something like that.
Yeah, Lisp and Scheme, actually, you just write the tree.
Yeah, exactly. And if you think about this, is also why a lot of tutorials and blog posts that explain how to write an interpreter they use a Lisp or a scheme as the input language because they do not have to worry a lot about the parser, because you're already writing your code as a tree data structure. All you have to do is take the parens and turn it into a real data structure, basically.
So it's just cheating. Like
Yeah.
Lisp is just a language where they didn't write the parser. They're like, you just write the tree for us.
Yeah, you could say that. Yeah, there's one famous article by Peter Norvig, and it's about how to write a Lisp interpreter in Python. And in this article, he doesn't write a lexer or a parser. All he does is he takes the code as input and splits the string on the parens, right?
Mm-hmm.
And that gives him enough structure, because it's already a nested tree form. That gives him enough structure to work with. You don't need a tokenizing process or like a lexer that tokenizes the input or a parser that turns it into a tree, because you already have the tree. You just need to make it a little bit more accessible by splitting the string on the parentheses.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. DigitalOcean stands out from the crowd due to its simplicity, high performance, and no billing surprises. Join a community of over 3.5 million developers on DigitalOcean. Sign up with a free $100 infrastructure credit at do.co/SERadio.
There are tools to help out with this. So I had used this Antler in the past, and it kind of builds a parser for you, to my understanding. So why do you hand build a parser if tools exist?
Good question. To be honest, like the short version is because I was fed up with others using tools to not build parsers. Because after reading a lot of tutorials and again blog posts about how to write your interpreter in a computer language, I was fed up with these black boxes. When it said in the text, and then we need to parse it. For that, we can just use this tool, and then next paragraph, okay, we're done. We now get from this tool an AST back. And that was for me like really frustrating, because I thought, well, what does the parser do? Like, I want to get down to understanding what this does. Like, I don't want black boxes. I don't want any magic. I want to understand everything. So is it a good idea to always write your own parser? I don't know. But if you want to understand how languages work, and that includes for me understanding how parsers work, then yes, it's a good exercise to build your own parser, right? It's the same, for example, if you want to learn how a web server works, you're not going to say, I'm going to use another web server. No, if you're there to learn something, you're going to implement it yourself, because that's a really great way to learn about the stuff. But yeah, if you just want to use stuff, you can use other tools that generate a parser for you. Yeah.
In your estimation, like what percentage of like real world interpreters use like some sort of tool, and what are like hand rolled?
That's a really interesting question, because the answer is funny. I would say 50% from what I've seen. And I'm saying it's funny because whenever somebody posts a tutorial about how to write a parser, or says this is how you can write your own parser in a blog post or stuff like this, then there will always be one or two people saying you shouldn't write your own parser. Like, just use a tool to generate your parser. Nobody, like, this is a solved problem in computer science for 40 years, and just use a tool and you don't have to worry about it. And I guess they're right to an extent. But then you look at the real implementations of programming languages, for example, Go, right? And then you realize, oh, they wrote their own parser. That's interesting. Why did they do that? Like, these are not dumb people writing Go, right? They're pretty smart. So why did they choose to write their own parser? And it turns out there are legitimate reasons for this, because if you use a tool to generate a parser, you end up with generated code. And as we all know, generated code is like rule of thumb, not the most beautiful code, right? It's generated code. Like, there's good generated code, but as a rule, you can say it's not as readable as handwritten code. And then it's also not maybe as optimized for your specific use case as you want it to be, or it contains too much for your specific use case, that you have like extra baggage that comes from this generic tool that doesn't really understand what exactly you want, because it's not built for your exact use case. So you can hand roll, or so you build your own parser that is really tailored to your specific use case, and it's easier to understand most of the time, and it's easier to maintain because you only write code. You don't write code that generates other code, which is like this added layer of indirection, I would say. And you can test it more easily, I would say. And that's usually what I hear why people choose to do this. And there's it's not a small number of languages that have this, I guess. Or let's take an example from the other side. The Ruby programming language does use a generated parser, and it uses a tool called Yak, which is I guess 30 or 40 years old. Like, it's a parser generator, and it takes in a so-called grammar file that specifies what your language looks like and what the parser should recognize and what it should turn the input into. And these are, these grammar files are written in their own language. So you have to know basically this DSL in order to be able to read and understand them. Now, in these grammar files, you often mix this meta language or DSL with some of the code that you want to have generated. So in the case of Ruby, you have this grammar file that contains bits of Yak's language and bits of C code, which is what the Ruby interpreter wants to generate. And this file, in Ruby's case, it's basically a black hole. Like, nobody dares to go near it. Nobody dares to touch it, because Ruby has a really, really flexible syntax. And this line, I don't know, this file is, a few thousand lines long. And I don't have the exact number, but it wouldn't surprise me if it's, 20,000 lines long or something. Like, it's a really monstrous file, and it's hard to maintain. Nobody understands it. Maybe one or two people understand it, but not a lot more. And, if they had built their parser by hand, there's no guarantee that it would be better. But, I would bet that it wouldn't be this, this monstrosity that depends on another tool and basically two languages that you need to learn in order for it to understand, and would probably be, easier to understand and maintain.
And like, it could be written in C, where there is, like techniques for abstracting and grouping things, where like the Yak grammar, it's not a full-fledged language, right? So you don't have all the full power.
Yeah, that's I guess that's a nice point about DSLs or specialized languages in general. Like, what if you hit their limit? Like, it's not as easy to add another layer of abstraction or your own abstraction as it is in a general purpose programming language.
So at this point, okay, we've taken our string, turn it into tokens.
Yeah.
Turn that tokens into a tree.
Yeah.
And then, so what? Are we done?
No. Then this is where basically the magic happens, right? Now you have the tree in hand, which is just a representation of the input program. Now you need to interpret it. And in the easiest way, that means you just go over this tree, like you walk down the tree, or you go iterate over it and just execute what it says, right? And this is really easy to do. Let's say you have a data structure that has different child nodes, where you can say child node type equals print statement or something, right? Like, you can check if this child node is a print statement. Then you could basically interpret your program by going over the AST and going over every child node and checking, is this child node a print statement? And if so, then take the value that the user wants to print and print it by using the puts language, the puts statement, or the log statement of whatever language you just wrote your interpreter in. Or if it, if the AST says 1 plus 2, then you can say, oh, the user wants to add 1 plus 2. Oh, yes, we can do this. This is 1 plus 2, that's 3. Let's return 3, right? And then, somewhere else in the program, you take this result of this evaluation, which is what you're doing, and you then print it, I guess, or put it somewhere else, or save it to a binding or something. But interpretation itself is, it's actually really easy to do. Like, you just have to iterate over your AST or your code and execute and do what it says.
So in fact, the evaluation part relies on kind of the language that your interpreter's written in. It's kind of like, it's It ends up running it in the host language.
Yeah,
is that right?
Exactly. So you have the host language, which is the language that your interpreter is written in, and you have the guest language, which is the language that the input program is written in. And yes, there's this, the bigger the divide between the host and the guest language is, the more interpretation you have to do. So the more work you have to do. For example, you mentioned Python. Let's say in Python you have list comprehensions, right? It's a really, really concise way of, let's say generating lists, right? You can say, give me from all of these numbers only the ones that are uneven, add them to this list, and then give me the sum of this list or something. Now, let's say you write an interpreter for Python list comprehensions, but you write it in C, right? And now you realize, C does not have a really nice to use data structure called list. So now you have to write lists in C first in order, to be able to actually represent what the user program is saying that you want a list, right? And the greater this divide between guest and host language, the more you have to do. If you go down even further and you have you write your interpreter in assembly language, for example, then you don't even have a proper concept of, I don't know, let's say the functions or something. You basically just jump around from different labels to different labels, stuff like this, right? And then it gets really hard because then you have let's say your guest language has something called list comprehension with, I don't know, what else could there be, like multi-threading built in and stuff like this. All of these concepts that only exist in this guest language, which is on a higher level of abstraction, you could say, then they only exist there, and now you have to do real work to translate them, right? And let's say the divide is really small, and you translate, you interpret Python in Ruby, and Python and Ruby share a lot of stuff. Both are, have objects, both have things like list comprehension, even they look different, but you can really, it's easy to translate between the two. And then you just, you go through your code and you execute as it says, and execute as it says in this case is not a lot of work, basically.
If we have the statement like let x equal 7 and then print x, where do we store this value of x in our evaluation stage?
Right. Somewhere in memory, right? You need some kind of internal representation that can hold this kind of information. Let's say your language only consists of, let statements and numbers. So you can say let x equals 7 and let, I don't know, a equals 10 or something. Then you need some internal representation of numbers. And it could be really simple, right? It could just be the numbers that the host language has, basically. But if you evaluate the program, you see, okay, somebody wants to store something here. The user wants to store 7 under the name X. Then we, somewhere in the book, it's called an environment. It's a data structure. It's basically, let's say, a hash map, right? It's a mapping from name to value. And you need to store the value and their name somewhere so that you can later, if somebody says print X, you can access the number again. And, the more advanced the values you want to store are, the more advanced your internal representation has to get. For example, numbers are, basically existent in every language that you might want to use. But let's say you have something like, I don't know, a struct or something, right? The user says, this is my struct. It has 3 fields. And then it says, let person equals person struct with first name foo, last name bar, age, I don't know, 25 or something. And then your host language needs some, representation of this struct. It needs to map to the guest language so you're able to represent this. Or you need to do some internal translation to another construct that only exists in the host language.
So like if I said let x equal, and then there I have a function, right?
Yeah.
And so because your language has first class functions, and I don't know that Go does. I'm no Go expert.
Yeah, Go has first class functions. Yeah.
Okay. Well, let's pretend it doesn't. So then you're saying you need some way to store in your hash map like some representation of this.
Yeah. And then exactly. So this is a great example because a function is not as easily representable as a number. So in Go, for example, you could represent a monkey function by defining a struct, right? And then you can say, what is a function really? Okay, a function is, it has like arguments, right? Named arguments. It has A, B, C, D. It takes in as arguments. And it has a function body. And a function body is, okay, this is just an AST node. It's a sequence of statements that gets executed when you call this function. Okay, that's not too hard. Like you define a struct and you say, my parameters are a list of identifiers of names, basically, and a function has a body, and that is an AST node of program statements, for example. And then if you say, let x equals function ABCD with the body puts ABCD, that prints ABCD, then in your hash map, in your environment, you save a representation of this function, a struct with these two fields filled out, and you save it under the name x. And then later, if your program says, yes, let's call the function x, then you fetch x, the function, from your environment, and then you call it, which is a different thing, basically. But this is how you could represent functions.
Yeah, so you're actually storing parts of the AST in some sort of wrapper in this environment, which is in fact a dictionary that you're just carrying around, right?
Yeah. And I mean, this is a really, really simplified way of putting this. Like, it's not the most advanced of techniques, right? And there, again, the lines get really, really blurry because your question basically pointed us in this direction when you said, does Go have first-class functions? Like, because what your question hints at is that, can we represent a construct from the guest language in something that the host language has, right? If the guest language has numbers and the host language has numbers, no question about it. Let's just use numbers for, if we don't need anything more. But if we need to store like functions, like, then the question is, can the host language generate functions at runtime, right? Which is what we would need to do when we interpret stuff, because remember, we're not compiling. We're actually, generating stuff at runtime while we're executing or interpreting this program. And then we need to represent this. Can we use the host language for this? In Ruby, for example, you could create objects, or, a function or method in Ruby is just an object. So you could create objects in Ruby that represent your guest function, and then you could call those objects. But, in other languages, you do not have objects, for example, that you can create at runtime. So you need another data structure to represent your guest data structure, basically. And this gets really, really interesting the more advanced your implementation gets. If you add compilation to this, if you add JIT compilation to this, then you get in like the really interesting territory of how to represent certain things. And then you realize in the end, it's all about representation. Like
that's the secret.
Because compilers have, or the most advanced compilers, they have different representations for the same piece of program, and these different representations are different in the amount of detail they contain. For example, the first representation may contain a lot of detail. It contains syntactic stuff, for example, comments, basically, right? And then the compiler can throw compiler error and say this function needs a comment or something. But then the compiler takes this representation and turns it into another representation that does not contain comments, for example, and it does not contain user readable names. For example, it doesn't contain the name foobar. It only contains like name one or something, like an ID, an internal thing. And then it turns this representation into a really dense bytecode, and then it turns this into machine code, and then it optimizes this machine code because this machine code is easy to optimize, and then it executes this machine code.
So it's like a complicated language may have like many ASTs. Like it creates an AST and then it might create an optimized version of that, and then a more optimized version, and then
the word is internal representation. IR is the shortened form, and an AST is just a internal representation. Bytecode is another form of internal representation, and the most advanced compilers, they have different stages of this internal representation, because different stages can represent different details that are only relevant for a certain stage of compilation.
Interesting. So your language, you said it's like 3,000 lines of Go code, including tests. So do you know what percentage of it falls into these kind of three categories we've discussed, like lexing versus parsing versus evaluating?
Yeah, I think I would say let's leave the test aside and just say the code, the implementation code, and then I would say 20% is the lexer. Then I would say, I don't know, 50 or 60% is the parser, and then the rest is evaluation. Because the parser is, in the first book, it's the most complex thing in the whole interpreter, basically.
Interesting. What makes the parser the most complex?
I would say because it needs the AST as an internal representation. So I include this in, the parser. You could probably say, you can divide that in half and say the AST, it's like the definition of all the different nodes in this abstract syntax tree, takes up a lot of space, and then the parser takes up a lot of space. The more you add to a language, which means the more syntax you add to a language, the longer your parser gets, basically.
So your language, it's a real language, and it's like 3,000 lines. So are there other languages out there with similarly concise interpreter implementations?
Now that you mentioned it, I guess one of the most widely used languages that has really small implementation might be Lua, which I think at the time was like, I'm making stuff up, I guess, but it was like 20,000 lines of C code or something, or 15,000 lines of C code, which is not a lot compared to, a lot of other languages.
So what's the biggest, do you think?
I don't know, the GCC, like the GNU compiler collection. This is like 5 million lines of code or something? Like it's huge.
Wow.
It's huge. And then I would say the JVM, for example, is a beast because it does all of this advanced stuff, that optimizations, JIT compilation, stuff like this. And I guess, people always say that Scala is a really complex language because it allows the user to do a lot of different things, right? So it needs to be, if you want to do a lot of different things, you need to do a lot of different things. And that means, it takes up more code, basically. C++, I guess, is one of the most complex languages out there. And the compiler is, also complex, I guess. But I don't know any, concrete numbers, basically.
Yeah, well, it's interesting how these sizes vary, right? From Lua at a couple.
Yeah. And whatever. I mean, if you think about it, it really depends on what the language is able to do, right?
And so that goes back to your Lua statement, right? Because Lua is like a wrapper around C, right? So it kind of...
Yeah.
It exposes a lot of the...
Yeah, it exposes a lot of the... Or you can use a lot of the lower level stuff in the C standard library, in libc, basically. Or you can use syscalls, which, are the things that the kernel provides. But if you don't have this, then you need to be able to provide certain things in your language so you can reuse them. And if you have enough tools in the base layers of your language, you can use these tools to build other stuff on top. But you need to have a certain amount of tools in your toolbox. Otherwise, there's no way that you can add anything.
So I think that we kind of covered what an interpreter is and kind of some of the stages of it and some things about their size. So I wanted to ask you some more high level questions. Mm-hmm. What do I learn from writing an interpreter? Why should I write one?
Because it's fun. There's a bunch of other reasons, but let me just say that it really is fun to write an interpreter. It was basically the most fun I ever had programming, because it's really nice that you can write a program that does not depend on anything else. You're basically inventing things in the air. Like, you're saying, okay, I have nothing right now, but now let's create a string in this fictional language called monkey. And now let's create a program that takes in this fictional monkey language and it outputs hello world, right? You do not depend on a database. You do not depend on an internet connection. You do not depend on a huge standard library. You do not depend on third-party libraries, and you do not depend on your operating system. All you depend on is basically what's in front of you in the code. And it's really pleasant to work on programming languages because of that, because you're inventing the thing that you want to work with, right? It's I don't know. To me, it feels like playing with Legos, basically. Like you can make stuff up. But that's the fun part, right? But the more serious answer is that by implementing an interpreter, you learn about parsing. As I said, like it's a huge part of the interpreter. And once you understand parsing, you understand a lot of other stuff that's happening all around you when you're programming. And then you're able to create all sorts of different solutions for different problems. Let's say, you need to, I don't know, analyze some input that you get in your web application, right? Maybe it's complicated and maybe you can't handle it as it comes over the wire, and maybe you need it in another representation. Then yeah, you can use the knowledge you gained by writing a parser and write another parser that, parses the input, basically.
Yeah, so I have an example. Like after I read your book, I had to do something at work involving rules for when a library has like a potential security issue. And the rules are represented as like strings of version numbers, like less than, greater than.
Yeah.
So it could be like this library is safe if the version's like less than 1 or greater than equal to 1.7 or, greater than 7 and so on, right?
Yeah.
A bunch of ranges, right? It seems simple, but in fact, there's like a order of operations problem because you have a bunch of ands and ors.
Yeah.
And so immediately it clicked to me that this is something that you built in your parser, that you need to turn this into a tree.
Yeah, exactly. Like if you didn't know about parsers, what you probably would have done, or what I would have done, is you bring out this big fat hammer called regex, right? And you just try to bang away at it, right? And you add regex and stuff like this. And then you end up realizing, no, wait, there's an order to it. And that means in parsers world, it means precedence, right? So you're saying, okay, like the and thing that you have in your rules, it has a higher precedence than, for example, the greater than or less than. So this needs to be somehow respected, right? When I'm building this up, or then. And then once you have your rules, you basically you also most probably want to say, is this a valid rule? That means you need to interpret it, right? So you parse it, and then you have this internal representation of your rule, and then you need to make sure that all the parts that you need are there. Does every subcomponent of this rule have like a left and right hand side, like two versions? Does it have the less than or the greater than symbol in the middle, or is there another symbol in the middle? And you can go a long way with regex, sure, but you're most likely going to hurt yourself at a certain point, and you realize, hey, if I would have just known how to write a parser, this would have been, a lot easier. And yeah, perfect example of how you can use this knowledge and transfer it to another thing.
If people out there want to build an interpreter, like what programming language concept is out there like that doesn't have representation? Like what language should be built? Do you have any ideas for like a language feature that is interesting that doesn't exist? Or
oh, you mean if you want to have something unique or something in your language?
Yeah, so like Monkey has a feature that a number of languages do, but not all of them, right? Which is that you can assign if statements to values, right? Like it's a expression oriented, right?
Yeah.
So that's like not every language has that, but I think it's a great feature, right? So are there other features that you think that would be interesting?
What I want to implement is pattern matching, right? That like pattern matching is like a really concise way of representing basically conditionals, right? And it's really interesting to implement, which I don't know yet how to do exactly, but I've been thinking about this for the last couple of months, basically. But pattern matching could be its own thing in your host language, so that you implement pattern matching directly in the host language, or you could maybe translate your patterns into just conditionals in your guest language, and then you interpret those, right? There's different things to it. Then what's also super interesting is concurrency. If you add like a concurrency model to your language, there's a bunch of different models out there. For example, Erlang has like an actor model of concurrency. Go follows a model called, Go has Go routines, basically, which are something called green threads, which can talk to each other through channels, which would also be interesting to implement. Then scheme languages have the concept of coroutines, which are interesting, which allow you to, and I'm sure I'm saying something wrong here, but which allow you to basically stop execution or resume execution of your program under certain conditions, which is quite an interesting thing to wrap your head around. And in addition to that, there's all sorts of syntactic things you can do with the language. Like, what do you allow your identifiers to look at? Do you allow special characters, for example, like Ruby does, so you can put a question mark in your function name and stuff like this? And, all sorts of things. And maybe you add some funky data structure. Instead of just having hashes and arrays and strings and numbers, you add something else, like maybe the main data structure in your program is a tree data structure or something. And there's different languages where, for example, I don't know, let's say SQL it's its own programming language, right? And everything, like, it's a declarative programming language, so it has a really specific view of the world. It only has statements that allow you to describe how you want to fetch or manipulate data. So it's totally different than, a general purpose language. So maybe you can write a language that goes in this direction, like really specific to a certain use case, like a DSL, for example.
It seems like a fun area to play in, right? Like, we work with programming languages all day.
Yeah. So a lot of my readers, they wrote to me and they said, look here, I took your monkey language, but I added this. I added modules. I added concurrency. I added list comprehensions. I added for loops, which I didn't include in the book, and somehow a lot of people want. I added, a bunch of other stuff. Then another reader just emailed me this morning saying, hey, here, I took the thing from your book, but turned it into a BASIC interpreter. But it's my version of BASIC. I combine all of the aspects of BASIC that I like from different BASIC implementations and make my own. So there's so much creativity in this. And if I look through GitHub of all the projects that people sent me, where they took the BASIC monkey interpreter and then turned it into something completely different, you're just, astounded by the creativity. It's really amazing. And it's so much fun because, as I said, like, it's fun to work with because to a certain extent, you're only constrained by basically your knowledge of programming constructs and your creativity, and you can add a lot of stuff to your language that's not, that's really easy to implement, but nobody ever thought about it before. But you can if you just, have the imagination for it.
Well, that is like a really exciting thought. And I think it's a great place to end things. So, yeah, Thorsten, thank you so much for coming on the show. I really enjoyed your book. I recommend people check it out. Where can listeners find your book?
Yeah, you can find the book, the first one, Writing and Interpreting Go, at interpreterbook.com. And you can find the second one, the sequel, at compilerbook.com. And the book itself is called Writing a Compiler in Go. And, it's actually a real sequel. So you need to start with the first one to get the second one because they build upon each other. But yes, interpreterbook.com and compilerbook.com.
Thank you very much, Thorsten. This is Adam Gordon Bell for Software Engineering Radio. Thank you for listening.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio. Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.